Salut. Faire la carte? Non, Simona n'est pas là. Assez. Est-ce que ça marche? Est-ce que je commence? All systems go. Ready for takeoff. OK. Bon, bonjour tout le monde. Merci pour ce temps avant les vacances. C'est très sympa. Donc, je présente Martin Lawless, qui était un postdoc avec nous il y a 3 ans.
Oui, 2021.
4 ans. Et depuis, il a la possibilité de revenir chaque été pour travailler avec nous sur différents projets. Donc, il fait ça encore cette année pour le mois de juillet. Et aujourd'hui, il présente un peu ses perspectives en enseignement. Donc, il a un poste de maître de conf.
Oui.
Presque prof.
Plus ou moins.
Bientôt.
Oui.
À New York, au Cooper Union. Et je te laisse voilà.
Là. Merci, Brian. Bonjour à tous, je suis Martin Lawless et parce que mon français n'est pas le meilleur, I'm going to continue the rest of the talk in English. So I am Martin Lawless. I am currently an assistant professor of mechanical engineering at the Cooper Union, which is located in New York City. And because it is a small undergraduate research institution, we are presented with many challenges that we don't necessarily see at upper level research institutions. And so I thought I'd present a pretty cool talk here on how we can overcome those challenges and really bring ourselves into research success despite the limitations. So a little bit of a background for myself first, because it will give context for the rest of the talk. I graduated with my PhD in acoustics in 2018 from Penn State, where I worked with the Sound Perception and Room Acoustics Laboratory, working on 2 main projects. The first being on the auditory and reward response to different levels of reverberation. Specifically, I placed participants in an MRI while they listened to different concert halls, and I was able to look at the different brain activity, both in the primary auditory cortex and in the reward network, to see which different concert halls they liked or disliked. That was the project that was my thesis, but of course, funding doesn't always work out really nicely, and so what I was actually funded on was on office acoustics, a project on office acoustics in which I placed participants in different levels of distracting or fatiguing sounds while I measured their stress levels with heart rate variability and skin conductance, and I made them perform different cognitive tasks like math tasks or memory tasks and things like that. After graduating, I went to the Cooper Union, where I was a visiting assistant professor for 3 years. Now, this was a non-permanent position, so non-tenure track, and I really treated it like a postdoc for teaching, because I didn't have teaching experience prior to this, and so I was teaching 2 to 3 courses per semester and really developing my pedagogical model and expertise. But at the same time, I was doing research with students, because part of being a professor is doing research. And so I had 4 main projects when I was there. One on immersive audio in virtual and augmented reality applications. One on active noise control. I had one looking at musical therapeutic intervention, sort of exploiting the things that I found in grad school to help people after stroke. And then one on a dual stage muffler to attenuate exhaust noise. After my stint at Cooper Union, I came here to D'Alembert, where I was working as a postdoc with Brian. I was supposed to be here for a year. I wound up being here for only 6 months because I actually got a job at Maritime College for a permanent position on the tenured track. So while I was here, I worked with Brian and David primarily on the localization of real and virtual sound sources. And I took that to SUNY Maritime with me, where I continued to work on the sound localization training, and I also had research based in low-cost acoustics experimentation, as well as some pedagogical research as well. So I kind of started my pedagogical research at that point. And I bring all of these up and sort of go through each and every one of these projects because I really want to highlight that there are stark differences between research at a graduate research institution level and an undergraduate teaching institution level, right? First things first, we'll talk about budget, right? Where my advisor, so I only have approximate numbers for these because these were my advisor's grants and experience, but for my auditory and reword response project, my advisor had about $250,000 in startup funds. It was a 5-year project, and she had a PhD student, me, to conduct all of the work in the project. So it was my goal as the PhD student to really become an expert in the subject matter and apply it to this very long-term project. I had some time to do so. The Office Acoustics project was industry sponsored, so we had even more money to play with. We had about $500,000 for a conceptualized 3-year project, and there were multiple PhD students and master students to work on the nitty-gritty details of this project. So we had different aspects. I was the one that was working on the cognitive tasks, but we had someone else working on an active noise control solution as well. But we were all working together as a team. While my advisor had these research responsibilities, she also had some teaching responsibilities. But because it was a research institution at Penn State, it was relatively low. Only about 0 to 1 courses per semester. So not so much of a teaching load. In contrast, when I went to Cooper Union, now specifically this was a non-tenure track position, I was actually fortunate enough that they did give me some startup funds. I got a whole $5,000 to start my project and start my lab. And I spent it on the immersive audio project. I needed a good computer. I needed to buy some speakers. I needed to buy some microphones. I was able to spend it that way, and I had to be a little bit clever in how I did it. This turned out to be a 3-year project because it was the amount of time that I spent at Cooper Union. And during that time, I had 1 master's student for 2 years and 3 undergraduate students that worked for a total of 1 year. In contrast, the active noise control project had a $0 budget. No money for that. It only lasted 1 year, and I had 1 master's student and 1 undergraduate student working on the project. So students with not as much expertise as a PhD student. And then lastly, for the other projects, of course, $0 budget. This is going to be a theme going forward. Short projects, so 1 year, and only undergrads to work on the project. So really short term and really a short amount of time to both teach the students to do what I needed them to do, but also for them to execute something new. On top of that, I had a higher teaching load than my advisor would have, where I had 2 to 3 courses that I was teaching per semester. It's an undergraduate teaching institution, so the expectations for teaching is higher and the expectations for research is lower, but you still want to have high quality research to go along with the teaching to give yourself a good sort of package of being a good professor. And similar story when I went to Maritime College. $0 in budget, 1-year projects, and only undergraduate students. In fact, SUNY Maritime has no master's students whatsoever in engineering, and so limited to working with undergraduate students. And on top of that, now I'm teaching 4 to 5 courses per semester. And so that's why there are only 2 projects when I was at Maritime as opposed to 4 when I was at Cooper. And yet, despite that, at Maritime, I was awarded 2 very prestigious awards, one being the President's Faculty Award for Outstanding Scholarship, scholarship being the place word for research here, and also I was awarded the ABS Endowed Professorship in Mechanical Engineering, which was based on the research that I did. And so I was able to be successful, able to be publishing despite the high teaching loads and low number of undergrads. And so what I'm going to talk about in this talk is essentially go over some projects. We'll go through a case study of looking at the low-cost acoustics experimentation project, the dual-stage muffler project, and the immersive audio project, so that you could hopefully glean some strategies that I had as I was undertaking these projects and turning them into successes. And at the end, we'll go through some lessons learned of how you could maybe learn from my mistakes and do even better than me, hopefully. So let's start with the low-cost acoustics experimentation project. This was in collaboration with a lab tech like Julia and a collaborator of mine, David Wooten, who's another professor of mechanical engineering at Cooper Union. And I continued this project at Maritime College with Christian Vera, who was a senior at the time and a student of mine for 1 year. We also were able to publish some of this information in the Journal of the Acoustical Society of America. Essentially, the goal behind this was to create a way for students to complete laboratories at home during the pandemic. We have these amazing laboratories at Cooper Union. This is a process and controls lab. This was a vibration lab that we had set up, or a modal analysis lab that we had set up. But with the pandemic, we lost access to all of these labs because the students couldn't come into the laboratory to conduct these experiments. So we decided to send the experiments home to the participants, or home to the students instead. And we came up with this initiative called See You at Home, which was a way of creating laboratory kits. We got some funding for this, that we were able to construct these kits, buy equipment, and send it to each individual student. So we sent them sensors and components to construct electronic circuits. So they were given microphones and a microcontroller that we could use as a data acquisition device. And we also focused on data collection and signal processing. We sent them with a GUI that we constructed ourselves that the students could interact with the different parts of the signal chain. And so we used the Teensy 4.1 microcontroller to act as our DAC. And the reason we did that was because it has a very high clock speed, allowing us to have a very high sample rate of 12 megahertz for 16-bit bit depth. And on top of that, it has 41 pins that we could use for both input and output, 17 of which were analog. So we could have 17 analog sensors simultaneously. As an SD card reader, you could program it with the Arduino, and so you have a large community support online that the students, if they were going to be experiencing problems, they didn't just have to turn to us as the instructors, they could also turn to the internet fairly easily. There are some downsides with it. One being that it only accepts between 0 and 3.3 volts. So for us in acoustics, when we have sine waves that are going up and down, typically we put on a high-pass filter so that we can remove the DC offset prior to taking in the signal. You can't do that with a Teensy. You have to use a digital high-pass filter after the fact to remove that DC offset. And additionally, it has a limited amount of flash memory. Really, it came down to about a megabyte of RAM. So when we're trying to sample at not that high of a sampling rate at only 44.1 kilohertz, we were only able to collect about 2 seconds of data at a time. We're able to move that data off of the Teensy onto the computer using serial communication, but that's much slower than our sample rate. Going forward, you could also use the SD card slot in order to write faster and save it faster so that it's not staying in RAM as much with multi-threading. We couldn't do that at a time. We didn't have the budget to send SD cards to all the students, but it's something that is possible. The other sensors that we sent to the students were some electret microphones, some thermistors, digital accelerometer, voltmeter, resistors, things that they needed to create a circuit, transformer bridge, etc. So that the total cost of this kit per student was about $185, which wasn't terrible. But if you were only interested in doing this for acoustics experiments, which is possible, just for the acoustics equipments, it's $40. And that includes the teensy, which is about $25. So that's the majority of the cost here. The GUI that we created, open source, it's available. You could likely find it online unless they took down the hosting. I'm not in charge of that. It was a Python GUI that we used using Qt, where they could communicate with the serial, input settings such as sample rate and number of samples, record the data, send the data to the computer, plot the data, and save the data. Pretty straightforward, but it allowed some interactivity for the students. And we used custom C++ libraries on the teensy that were uploaded with Arduino to handle the data sending to and from the computer. So yeah, students were able to plot and see the data, not necessarily in real time, but immediately after they took their measurement. So we set the students with some pre-packaged experiments so that we could essentially get them used to the signal chain, get them used to understanding how the kit works, how the teensy works, how the DAC works. And so one of the pre-packaged experiments that we did was a speed of sound experiment, where we essentially used the time of flight method to determine how, what the speed of sound was in air. And we could do it at different temperatures. So we had our teensy connected to the computer, and we set up two mics, which I'll represent as mic 1 and mic 2. And the students were even sent a ruler in this kit so that we didn't assume anything. And with this ruler, they were able to measure the length of the distance between mics 1 and 2. They can then put an impulsive source on one side of mic 1 such that a wave propagates from mic 1 and mic 2, and we're able to measure the time it takes for the onset of the wave reaching mic 1 and mic 2, and we can calculate the speed of sound fairly easily as the distance divided by the travel time, or just L over T. Simultaneously, the students were using a thermistor to measure temperature so that we could compare our measured speed of sound to that of theory, where C is going to be related to the square root of gamma RT, or so C is proportional to the square root of temperature. So in order to calculate that time t, we used a visual cross-correlation. We could have done a calculated cross-correlation. We decided to do it visually so that the students would, again, from a pedagogical perspective, we're trying to teach them how this is done rather than just doing it for them. So the students would do a visual cross-correlation using a slider, which just shifted the orange signal here, one sample at a time. And they tried to line up the sample as best as possible. And we then calculated the time based on the number of slider steps it took to line up the signal, divided by the sampling rate. And we, for example, with 29 slider steps, we get a time between the mics of 6.58 times 10 to the negative 4 seconds, which, as we know, is fairly quick. But from that, we can calculate the speed of sound. And so here are our results. This was the results from every student in this 30-student class. Some did it several times, so that's why there's so many dots. And you'll notice straight off the bat, most of this was done in air at ambient temperatures, and we have some crazy ones in there. I think this one's about 475 meters per second for the speed of sound. And here, down here, even though, yes, we're at a colder temperature, 175 meters per second is a little bit low. This is our Goldilocks, right? This is where we expected, based on this temperature range, most of our measurements to be. And if we look at a histogram of all the measurements, it's a little hard to tell with all the dots on top of each other, but the majority of our measurements was in that Goldilocks zone. So we were able to get the correct answers. But we do have quite a bit which are above the speed of sound that we were expecting, and even some fewer, but that were not, that were lower than the speed of sound that we were expecting. Let's examine why. So the reason that it was higher, well, first let's look at a good measurement. A good measurement would be with the impulsive source exactly collineated with the axis between mic 1 and 2. And so this is me doing the experiment myself. I took the length to be exactly 9 inches, putting 1 and 2. I made sure that my source placement was exactly 32 inches from mic 1 and exactly in line with mic 1, as best I possibly could using my ruler. I measured the temperature to be 20.6 degrees Celsius, which would give us an expected speed of sound of 343 meters per second. Well, I found it was the same measurement that I showed you before with a slider step of 29, giving us a speed of sound of 347.6 meters per second. Well, even though they're not the same, turns out it's within the uncertainty of each other, right? This uncertainty stems from our calculation of C, where we could use the total derivative method to derive the uncertainty, and we find that the uncertainty is actually proportional to 1 over L, right? So the closer the mics are together, as we expect, the more uncertain we are. The further the mics are apart, the more certain we are in our measurement. So what happens when, say, a student isn't as precise? I moved my hands 3 inches perpendicular to the axis of collinearity, and I took the same measurement, and I found that the number of slider steps changed because the propagation path is no longer a plane wave, right? Because the impulsive source is actually spherical. It reached mic 1 faster than I expected, and I was able to calculate, or really reached mic 2 faster than expected, and I was able to calculate a speed of sound of 373.4 meters per second, which is not within uncertainty. So what we learned here was that, one, we need to place the microphones further apart to be more certain in our data, and also have more precise source placements. And so that pretty much just comes down to instruct the students to do it better. On the low side of things, we likely think that the low calculated sound sources were likely due to poor visual cross correlations. Some students were likely lining it up with just the first peak, but as we can see here, this peak on orange likely belongs with this peak, this lower peak on orange likely belongs with this lower peak, and so it changes the amount of slider steps that were needed, which drives the speed of sound very low. This also probably contributed to the higher ones as well, but was most seen with the lower ones, definitely. Even though the uncertainty is better. And so, how do we fix this? Louder source so that it's really clear what is the peak in the signal, and also we can verify. I mean, hindsight is 20/20, right? We should have just put in the calculated cross correlation from the get-go in the GUI. Very easy to fix. So what I talked about right now is really is pedagogical research. It's not so much so research that I'm doing with students, but really using students as participants to take data. The way that you can use students inside the course is to implement what's called project-based learning. And project-based learning is essentially giving the students a topic that runs concurrently with the subject matter of the class. So for example, you might be teaching a dynamics class, and while you're doing projectile motion, you might have them take measurements and do a projectile motion experiment at the same time. The way that I implement project-based learning is by making students work with a client, and the client and the student sort of come together and define a problem statement that is related to the course. And then the students are then instructed that they have to construct instrumentation to solve that problem in one way or the other. And in this case, I, as the instructor / advisor, I was serving as the client. I had a problem that I wanted to be solved, which was my research that I then, during the context of the course, set off my students to do. So I had two during this semester that I particularly was interested in. One, I was interested in measuring the absorption coefficient of mycelium panels. right? Where we could put mycelium and grow our own acoustic panels, perhaps. And so the students created an impedance tube to measure the absorption coefficient of different materials. And then the other one was on the Doppler shift and seeing if we could demonstrate it. I'm not going to talk about that one today just because of time, and we'll focus on the impedance tube experiment. So the impedance tube experiment is based on the standing wave ratio, where when a wave comes in and interacts with a material that is neither rigid nor open, the impedance affects how much of a pressure maximum and pressure minimum we see in this moving standing wave. So it's not a standing wave per se because it moves, but we still see pressure minimum and maximum. And we can calculate the standing wave ratio as the ratio between the maximum pressure and the minimum pressure. And if we're using the same microphone throughout the whole experiment, we don't have to worry about mic sensitivities or calibrations, and we can just look at the ratios between voltages. We could then calculate the reflection coefficient by looking at the standing wave ratio at the wall itself and calculate absorption coefficients based on the reflection coefficient. And so the students created a setup where they used a PVC tube to act as the impedance tube. There's a D there, but there's a driver to send a signal down the tube, an end cap that has our material in it, a steel plate to serve as a very rigid wall on the other side of our material, and a microphone that went through a hollow tube so that we can move the microphone back and forth, and the students would know exactly where the microphone was with a ruler that was placed on the tube, or drawn on the tube. This added some cost to our kit. In order for the students to assemble these materials, they needed an additional $78. That $78 actually mostly came from the steel plate. We needed a pretty thick, heavy steel plate at the end of the cap, so I think that alone was about $40 to $50. It was pretty hefty. And we were able to take some data on a Jardin acoustic panel, which has an average absorption coefficient of about 0.8 between 500 and 2000 hertz octave bands. The students took these measurements at 400, 800, 1200, and 1600 hertz. The reason they chose these frequencies was because they were sort of running up to the deadline and didn't consult me and ask which frequencies to test before they just went ahead and did it, but that's okay. We were then able to calculate the standing wave ratio by interpolating what Vmax, the pressure maximum, and Vmin, the V minimum would be at the wall, and we can see it's fairly constant for the maximum, but you need to do a linear interpretation for the minimum. And we were able to calculate absorption coefficients with uncertainties for each of these different sine waves and calculate an average of 0.84 plus or minus 0.04. So that we had pretty good agreement between what was reported by Jardin and what we measured. And I think it just looks really cool that we were able to get these high fidelity acoustics measurements with this low cost equipment for $120, like all told. Continued this experiment at SUNY Maritime College. I put in an additional expense for a calibrated microphone of $26 because I would want to take this method and maybe do sound pressure level experiments with it, and you need calibrated microphones in order to do that. And so I purchased a $26 calibrated microphone so that we can place the two microphones very close together so that we can calibrate our electret microphones, because there's not a really commercially available calibrator for electret microphones. We built this anechoic box because I no longer had an anechoic chamber at my disposal, which we made out of plywood. We put in 9 inches thick of insulation. We just used a computer speaker because I ran out of budget once I spent the $26. And this time we used a Raspberry Pi Pico for the DAC instead of a Teensy. It's very similar. We were able to put use the exact same GUI, use the exact same custom libraries that we built, except it was only $4 instead of $25. And there's our microphones in this setup. and we found that we were able to get pretty good acoustics measurements out of it. You could see we were playing just a 1,000 hertz signal out of the speaker, and you could see that there was some noise in the signal, but really there was a lot of there was a strong peak at that 1,000 hertz, so we were able to calibrate the signal based on the 1,000 hertz signal, and we were able to measure a sensitivity of about 0.0012 volts per Pascal for the electret mic. The manufacturer quotes 0.0089 to 0.0126 volts per Pascal, so we weren't in this range. There could be several reasons for this. One being maybe the electret mic that we used, they get broken really easily. You can crush the membrane really easily, so we might have lost sensitivity that way. The other thing that it could be is that something was wrong with our setup. We could have done something wrong. And the unfortunate thing is that at this point, the student graduated and I had no one else to work on it. So let's see what some of the lessons were learned. One, we can use low-cost equipment for acoustics research. We were able to get high-fidelity data from our impedance tube and even from our speed of sound experiment, even if it wasn't exactly correct. In order to get research out of students, the best way that I found to work with them was to integrate it with their coursework. Undergraduate students in particular have a high course load. These students had 18 to 22 credits per semester that they were working with, which is about 6 to 7 courses. And so if you can integrate it with their coursework where they're trying to get a good grade, you're going to get better research out of it. So project-based learning is a great way to do that. And then being aware of semester deadlines, right? Students are going to be only able to work on it up to the end of the semester. They're going to have no motivation to work on it afterwards because they got their grade, they're done, they're moving on to the next thing, they have enough work to do. And so your work may stall when the semester is over, but it also means that when they're coming up to that deadline, they may take some shortcuts that you don't exactly agree with, you have to work with, and then hopefully go back after the fact to correct. So the second study that I'm going to talk about today is using a dual stage muffler to attenuate exhaust noise. And I'm going to tell you right away, I went into this project knowing nothing about exhaust noise. I went into the study knowing nothing about mufflers. But Yuval, the student that I worked with, came to me with a problem. He worked with the Formula SAE team and they needed to attenuate their exhaust noise. They needed to have a SPL limit of 103 decibels while it was idling, and at all other engine speeds, including their max engine speed, they couldn't exceed 110 decibels. And this was a problem that he had. And he came to me, he's like, oh, I know you're an acoustics person, can you help me with this problem? And I really wanted to help him, but I didn't want it to take time away from my own research, right? I was doing things with immersive audio. I was doing things that were quite different from this. I'm very glad that I went and decided to help him because it wound up being a very interesting research project that we did, but we needed to make sure that we set the expectations so that it became a research project and not just the creation of a muffler. So what I learned along the way was that mufflers do attenuate sound through expansion chambers, and essentially what happens is because there's a difference in the cross-sectional area between the normal exhaust pipe and the muffler itself, the acoustic wave experiences a change in acoustic impedance. There are then internal reflections that occur within the muffler, and our transmission to the next part of the exhaust pipe decreases because of the difference between the cross-sectional area, the wave number K, and the length of the expansion chamber. And so we could see if we had all the room in the world, if we could have S1 be as big as possible, we'll have the best amount of transmission loss. If we could have L be as big as possible, we'll have the bigger amount of transmission loss. But of course, we're restricted by the size of the car. And so with our initial conditions, that our initial cross-sectional area is about 7.1 inches squared, we constructed a primary chamber, primary muffler, which was completely hollow on the inside, had a cross-sectional area of 113 inches squared, so about a 13.5 to 1 ratio between the two, and a length of 12 inches. And a secondary chamber, which was a little bit smaller, at 28.3 inches, so not as much. But what we were able to do with this one was create a perforated inside so that we could pack the inside of it with absorbing material insulation to hopefully absorb the sound as it passed through. I still had an anechoic chamber at this point that I had at my disposal, and so we were able to construct a lab setup where we had a speaker to send a noise signal down the exhaust pipe that we were able to pick up with several different microphones. Again, limited by cost, so our speaker doesn't have the greatest frequency response, but it was good in the frequency range of issue. The engine had an RPM which was outputting about 250 hertz. This is sort of the full setup with the primary, and we have an inlet and an outlet mic, and here's the secondary with the inlet and the outlet. And we even did a case where the primary and secondary were placed together. We couldn't have a long pipe, so we did put a curve into the pipe, and again place the inlet and outlet after both chambers. And here are our results. We could see when we just had a straight tube, there was little to no attenuation. With the primary chamber in blue, we had fairly good low frequency attenuation between 10 and 20 dB. The high frequency attenuation started to go down a little bit, which was a little bit surprising to us. But that was okay because the secondary chamber with the acoustic insulation inside was very good at attenuating high frequencies. And then, so when we put them together, we had the best response. We're at our frequency range of issue at the 250 hertz octave band. We had about 25 dB of attenuation. We put this into practice, so Yuval actually took this muffler to the competition in Michigan, where he was able to trade in the off-the-shelf muffler that they were using with this primary and secondary muffler, and we could see that we got about 17 dB of improvement over the off-the-shelf muffler, and so our system worked fairly well. And at the end of the day, he was able to submit this to a conference for presentation, and he won the Best Student Paper Award for the Physical Acoustics Technical Committee, which was great because he was an undergraduate student competing against master's and PhD students for that award. So fairly successful publication. So lessons learned from this project. First, have your mind and door open to new ideas from students. I would never have done this project without Yuval as the person to come to me and say, hey, let's do a project. And so when you're doing this, your students are going to have all sorts of other commitments to do. They're going to have all sorts of other responsibilities. And so if you could get them to commit to a project and really enjoy working on your project, it helps a ton. And so if I had given Yuval a different project to do, he wouldn't have been as interested in it because he had this other thing to do, and we wouldn't have gotten as much done. It requires a little bit of flexibility. And then second, as I mentioned, you need to make sure that you're setting expectations for the student and making sure that they're reasonable, because this undergraduate student has a limited amount of time, but ultimately this research needs to benefit you and your career as well. And so making sure you're encouraging the students to publish and present and go from, okay, let's just create this thing, to actually let's just do a real project and real sort of measurements on this thing, will really be beneficial to your work. And last but not least, let's talk about immersive audio and VR. So this was a many-year project with many people. It started off as a master's thesis. It moved on to a senior design project in mechanical engineering and a senior design project in electrical engineering. Once I left Cooper Union, I started collaborating with David and Brian here on similar work, not exactly the same. And then we took the work from D'Alembert and did some things at Maritime College with 2 undergraduate students. The motivation behind this project being this is what I was interested in, first off. This wasn't what a student came up with. This was what I was interested in it. And the motivation being that it requires, VR and AR requires spatial audio to enhance realism, right? We're pretty good with visual realism right now, and the physics of the engine, but really having that spatial audio over the headphones, it's not quite there yet. And it has tons of applications in aviation and medicine. Even here, working with Charlotte and Brian and David on a virtual acoustic environment rehearsal tool for musicians. It also helps connectivity. This was the electrical engineering group in which we created spatial audio within a Zoom meeting, right? All sorts of different applications for spatial audio. And just, I'm sure many of you are aware of this, but just to go over, in order to actually achieve spatial sound, we alter monaural sound with a set of binaural filters called a head-related transfer function, and they're based on the source location in space relative to the head. Because when a source propagates sound, it could reach the right ear in this case faster than it reaches the left ear, and so the signals that we measure at the right and left ear can have an interaural time difference associated with them. We could also see that the head can mask part of the sound and obstruct part of the sound that is reached in the left ear. So we also have an interaural level difference that we can measure between the two ears. And these two quantities, ITD and ILD, are very much correlated with head size. Similarly, when the sound comes in and it interacts with our pinna, which is the structure before our sensor, it reflects off of the different folds in our pinna, which is the cause of these different reflections that we see in our signals. We experience this as the different spectral content that we hear when we hear a noise, different timbral effects that we can hear. And these are going to be based off of different pinna features. Because everyone's pinna is different, your HRTF is different from my HRTF, and it's hard to individualize each individual HRTF. So before I came to D'Alembert, we were looking into how we could use machine learning and leverage machine learning into predicting someone's HRTF based on their head size, based on the shape of their pinna. And so included in one of the HRTF's data sets is anthropometric features of pinna shape and head size that we could then put into an artificial neural network, train it based on this data set, and output the HRTF at all of these different positions, the HRIRs at all of these different positions. And the studies that we were basing this on had very promising results, right? Our input to the machine learning model was 37 features of head and ear shape. We used 5 hidden layers. Well, actually, this study used 5 hidden layers, and output of the 200 sample HRIR. And they showed, hey, look, we had one model at negative 45 degrees azimuth, 45 degrees elevation, and we had very low root mean square error. We did a great job, and they left it there. So we tried to replicate it. And we had the same model as them, except we input the azimuth and elevation so that it wasn't just one location that we were looking at. And when we did that, we found, well, that doesn't look as great. Even though our root mean squared error, which is the error function, the cost function that we use to validate the model, even though that was a lot lower, we could see they don't match up as well, and we have shifted peaks here, causing an error in that interaural time difference. On average was about 3.7 samples. So what do we do? So we decided to use a 2-model approach to eliminate some between subject measurement errors. So first off, we took that right signal. Well, actually this was left ear, right ear. I changed the ears, so that's okay. We treated the symmetry in the ear so that left ears could be right ears, and we basically inverted everything so that we can essentially double our data set at that point, treating right ears as left ears. We time aligned based on the onset of the onset threshold, all of our signals, and so that we can now have two models, the artificial neural network to focus purely on the ear shape, the pinna shape, and where the reflections are, and a regression tree that we could use for ITD to estimate that delay that is going to be based on head size and ear height and things like that. And when we do that, we improved our results. So this was our prior result that was based on the first model that I showed, and then our new model improves in root mean squared error, and it improved in ITD error as well, maybe within just noticeable difference. And we could see that they match up a lot better, so we wanted to test to see if this perceptually made sense. We created our own localization task. You'll see that this was prior to me coming to D'Alembert, and the localization task is not as refined as the one that we have now. But essentially what we found was that the participants didn't perform any better with their estimated HRTF to a generic HRTF. There was no improvement. And so there still was work to be done because there were no perceptual differences for these HRTFs. Likely this is because of the small number of data sets in our samples. And so the CPIC data set has only 45 participants, even though it has a lot of source locations. Independent variable or independent participants is only 45, and that's simply not enough for machine learning, where we need tens to 20,000s worth of independent samples. All the other popular HRTF databases at the time also do not have enough participants in it. And the problem is we can't combine them so much because the source locations aren't necessarily the same. And so we still don't have independent source positions as well. Even ones that have come out since then, widespread being the most, but widespread doesn't have any anthropometric features associated with it, and it's still only 1,000. Sonicom, which I think is still building its data set, has about 200 now. It doesn't have anthropometric features, but it does have pictures, so we can at least get the anthropometric features from the pictures. But it's not enough. So what I decided to do at Cooper was construct my own mini HRTF measurement setup. We have a very small chamber there, maybe from here to the end of the table. It's a very small acoustic chamber, but we can create our own mini setup to hopefully come up with a model that we could at least validate with our setup. And after 1 year of work working with the senior design capstone team, we built one speaker, and we built our microphones that fit in the ear so that we were able to measure an HRTF, and that was it. We had one speaker. And I wanted to continue this, but as it turns out, I no longer had a position at Cooper Union, and I wasn't able to work there any longer. So it pretty much made all work on that project stall. Luckily, I was able to come here. So through some networks and collaborations, I met Brian and David, and I was able to continue the work on sound localization. We worked on some sound localization training where we are exploiting the proprioception, where we can have participants use their hand to play a sound. Audio didn't work, that's okay. But they play a sound from a certain location, and they can associate that sound with the location of their hand, because our brain is really good at knowing where our hand is in space at all times. And so by moving our hands around and having different sounds represented by different colors here at each of those different locations, we could actually train our brains to accept someone else's HRTF. And we could use different source positions to have different sounds that the participants can compare and try to find the right one. Training usually occurs over a course of 3 days, where we first give them a localization task to see how good they're doing. That's the L0 here. And then we have them train using that setup that I just told you. Again, much prettier localization test now, thanks to David. And then we test the localization at the end of each day to see how they progress as well. And what we found was that, I took a slide out because I was running out of time, but sometimes this works, sometimes this doesn't. And so at Maritime, what we wound up doing was trying to gamify the experience a little bit, such that we added in a health bar, so that if you got the answer wrong, you saw the health bar go down, shot clock, so that you only had a certain amount of time to answer, and then as we see the shot clock run down, we'll also see that the color of the balls change to give a sense of urgency in the experiment. And again, that took 1 year. Again, I'm really proud of the work that they did here, right? These were undergraduate students that came in with zero coding experience. They've never coded before, never worked in Unity, never worked with acoustics, didn't know what an HRTF was, didn't know what a sine wave was, right? And so to get to this point in 1 year was quite an accomplishment for them, and I'm very proud of them for what they did. But it did mean that I had to be patient, be persistent. The work that you're going to be doing is going to be incremental. So now that I'm going back to Cooper Union, I'm no longer at Maritime. I'm starting at Cooper Union in the spring. I'm going to be using some of the tools that I learned here at D'Alembert, going back to that mini HRTF system, and actually going back to this machine learning project to bring it all together. So again, being patient, being persistent. It's going to take longer than what you may be used to here on the high tier research level, but you can make incremental progress. You can be publishing papers. You can be getting things done. On top of that, networking and collaborations are key in this regard. Networking and collaborations are important at research institutions, right? A lot of research doesn't get done that way. But specifically for teaching institutions, I wouldn't be where I am today without the help from Brian, without the help from David, and all the people that I work with here. It helps you keep up with the current research. And while publishing might not be as important for tenure, depending on the university that you're at, the publications help you increase your engagement with research for students. And that's going to be very beneficial for them, keeping them in the acoustic community, for them to go out and do cool things and cool research that you could collaborate with later. But also, it's from a pedagogical perspective, it helps them learn the material. With that, I'll leave it there. Thank you very much for listening. And I'm happy to take questions, but we'll use the mic if anyone has questions. Oh, thank you.
Thank you very much for your presentation. I was very interested by the first projects you've shown in your presentation, because actually I'm doing almost the same for master students here, but they've never done acoustics before. It's another master. So I was very interested by the little microcontroller you've introduced, and I had just one question about how did you plug it to the different components, because I haven't seen any pins on the chip.
Yeah.
So I think you've sketched sort of a square, which is a board maybe, I don't know.
Yes.
And then you need to solder things.
So this is a breadboard here. And so the pins are, again, it's allowing the students to sort of play with the different circuit layouts, but essentially the pins here go into the pins on the teensy itself. The teensy has, well, there we go. So these circles here on the side, those are our pins for input into the teensy, and then you can solder in
so you
some
need to solder them
headers.
before?
You can solder in some headers before, yes.
Because they can't do that at home, I guess.
Yeah, some students did do it at home. Some we had to wait a little bit and send it out.
Okay, good. Thanks.
Yeah.
Thank you very much for your talk. You don't explore the evaluation of the teaching and the, I don't know the name in English, compétences in French. And for some projects, how you do this evaluation?
Yep, absolutely. So for this project in particular, for the teaching, we had assessment in which we tested them at the beginning on their base knowledge, essentially. In the middle of the semester, we got feedback from them on the different concepts of uncertainty and statistical analysis. And then at the end, we asked them to evaluate how well these specific projects contributed to the learning. And so I tried to focus more on the less pedagogical research in this talk, but essentially what the students found was that the projects gave them a deeper learning for the experimental setup and for the experimentation aspects of the course. And so the project-based learning was really effective, specifically at having them really think about the instrumentation that they needed to use for their projects when it wasn't just given to them and told, prepackaged what they have to do. So yeah, so I do have a citation here. In that the pedagogical research is part of that publication. So happy to talk with you more about it. Yes, lunchtime. Thank you all for coming. I appreciate it.